Hi, this is your lesson on the periodic table of elements and the electron configuration of ions. You may have been given guided notes. If you haven't, you can certainly take notes in your notebook. But if you're given guided notes, I will be cueing you to when to fill in certain parts of those guided notes. So just a sort of evolution of the periodic table. In 1829, a scientist named J.W. Dobereiner noticed that he could group certain elements by similar chemical properties. And this was the beginning of scientists trying to decide and understand how chemicals related to each other. In 1869, a Russian scientist named Dmitry Mendeleev actually did the most in terms of starting to really look at putting the elements in a periodic table based on their average atomic mass. Since the nucleus had not been theorized or discovered yet, they could only figure out the average atomic masses, and he arranged the periodic table based on that. But there were a couple of notable problems with his arrangement that were solved once we understood the idea of the atomic number, or the number of protons being the identifying number of the element. And the modern periodic table, with lots of holes in it that we filled in as we discovered more and more elements, was formulated by a man named Henry Moseley in 1913. So you may want to fill in your notes where those arrows are, each one of the notations: similar chemical properties, average atomic mass, and average atomic number. So again, Mendeleev was the first one to kind of try to start to arrange them. And you note that this doesn't look too much like our modern periodic table, but he is trying to arrange them based, you'll notice, on the masses as opposed to the atomic numbers. Like, for example, the atomic mass of carbon is 12, and we know the atomic number of carbon is 6. But he was trying to get some order, and it has become a very useful tool for chemists. The modern periodic table looks like this. It's arranged by atomic number, and the atomic number you will recognize, usually there's a key on your periodic table, you'll recognize because it goes from top to bottom, left to right, in order. Hydrogen has 1 proton in its nucleus, helium 2, lithium 3, beryllium 4, and you just keep going. Okay, so here are a few fill in the blanks. What is the periodic table? Well, it shows all the known elements in the universe, and we're now up to 118 known elements. It organizes the elements by chemical properties. A great deal of information about an element can be gathered from its position on the periodic table. For example, you can predict with reasonably good accuracy the physical and chemical properties of the element. We spoke about this earlier in our video on reactivity of metals and nonmetals. You can also predict what other elements a particular element will react with chemically. So, for example, chlorine, bromine, and iodine are all halogens, and they have similar chemical properties. They are relatively reactive, they vaporize, as you can see, and they form compounds in similar ratios with metals. Now, on your periodic table, as you've labeled from a previous assignment, you know there are 3 types of elements on the periodic table: metals, nonmetals, and metalloids. So you should be able to recognize some general properties of each one of these types of elements. Metals are good conductors of heat and electricity. All metals, except for Hg, which is the symbol for mercury, are solid at room temperature. They have a high luster and sheen, and they are ductile and malleable. And if you don't know what those mean, you may want to jot down the definition. Ductile means you can draw metals into wires, like you can have copper wires. And malleable means that you can mold them. You can bend them, you can shape them, and they will not break or crack. All right, so those are metals. Nonmetals are poor conductors of heat and electricity. Think diamonds. Diamonds don't conduct electricity, Nonmetals are mostly gases at room temperature, though. Think of the halogens, think of the noble gases. They're mostly gases at room temperature. Now, their physical properties vary greatly, but if they are a solid, they are brittle. And what brittle means is they will break, they will crack. Think about taking a piece of coal or a piece of graphite, which is just carbon, and trying to bend it. You wouldn't be able to, it would just break. Now, metalloids are along that stair step that is indicated on most periodic tables. They're sometimes called semimetals, and they have characteristics of both metals and nonmetals. For example, silicon is a semimetal that is a semiconductor. It does conduct electricity under certain circumstances, but it's also very brittle and will just shatter as opposed to bend or be drawn into wires. So make sure you have filled in all of those slots on your guided notes. So again, when you look at the periodic table, just like you labeled in an earlier assignment, most of the elements are metals. Along this stair step here, you find the metalloids, and then over here, you find the nonmetals. The only nonmetal that's not here on the right is hydrogen, and hydrogen is just really weird. It only has one proton and one electron, so it kind of sometimes has some reactive characteristics of group 1, but mostly has reactive characteristics of group 17. So it is a nonmetal. All right, now we did this in a previous lesson, but let's do it again. Periodic law. When elements are arranged in order of increasing atomic number, there's a periodic repetition of their physical and chemical properties. The elements within the same column have similar properties. This is because they have all the same number of valence electrons. The elements within the row that's going across, sometimes it's called the period, repeat predictable patterns as you move from one period to the next. Now again, let's make sure we know our vocabulary. The columns are called groups, and they represent the sublevel of the last electron of each element in that column. So in here, we've got the 1s, the 2s, the 1s1, the 2s1, the 3s1, and so forth. But these columns, and they're labeled on your SOL periodic table, are known as groups. And as we learned in previous lessons, 4 of those groups have special names. We'll go over that again. The rows are called periods, and they represent the energy level of the s valence electrons that reside in this row. So the first row is the first energy level, second row, the second energy level, the third row, the third energy level, and so forth. All right. Now, we talked about this and you labeled this. There are some sections that you need to know. For example, group 1 are the alkali metals, and group 2 are the alkaline earth metals. This section right here in between 3 and 12 are called the transition elements or the transition metals. The group 17 is called the halogens, and group 18 is called the noble gases. And you can see sometimes you will have the electron configuration here. You'll have the atomic number. You can tell it's the atomic number because it goes in sequence, 1, 2, 3, 4. You'll have the atomic mass, the average weight of an atom. That will almost always be an atom with a decimal because it's a weighted average. All right, now we can predict valence electrons from the periodic table. We learned this shortcut last time. If you're in group 1, you will have 1 valence electron. Group 2, you'll have 2. Group 13, you'll have 3. Group 14, 4, and so forth. The only exception is helium here, even though it's in group 18, only has 2, and that's because the first energy level only has 2 valence electrons. Okay, now we're going to do a little introduction to ions. And so hopefully you have filled in all your notes regarding the names of the families and their groups, and also the number of valence electrons. So remember, chemical reactions are driven by wanting to have a stable outside electron configuration, and the most stable outside electron configuration is that of noble gases. So if you have a neutral atom and it loses electrons, it'll become a cation. If it gains electrons, it'll become an anion. But because of the valence electrons, there's a predictable pattern that we're going to go over. So what does every atom want? So please fill this in. It wants to have a full outer energy level. It wants to look like a noble gas, have the same number of electrons as a noble gas. Atoms form ions to achieve this. This is the driving force of chemistry. They want to achieve full s and p orbitals, and this is called the octet rule. Circle, underline. Everybody wants 8 valence electrons. Remember, you have S2, P6, that's 8 electrons. Everyone is moving towards trying to get 8 electrons in their outermost energy level, just like the noble gases. The most common ion charge, or the most common oxidation state, those two words are interchangeable, is where the atom has a full outer energy level. So an atom will not just form any old ion. It forms a specific ion because it wants to get that octet. Now, metals lose electrons, becoming cations. Cations are positive, remember? If you lose something negative, you become positive. This is a process called oxidation. Nonmetals gain electrons by becoming anions, and this is a process called reduction. So we're going to fill in and talk a little bit about the behavior of metals versus nonmetals. Here are metals that are representative of group 1, 2, and 13. And here are their electron configurations. You can tell from their electron configurations or from their position on the periodic table the number of valence electrons. And remember, we're going to go through sodium here and take a look at this. And remember, sodium wants to look like neon. So what's the easiest thing to do in a chemical reaction? Well, with its 1 valence electron, it's losing 1. If it loses 1, it has 1 less negative charge. It becomes positive 1. It then looks like the noble gas neon. And again, just so we start learning this vocabulary, losing electrons is called oxidation. Metals are oxidized. They lose electrons. Now let's fill in magnesium and aluminum. They have to lose more electrons to look like neon. For example, magnesium has 2 valence electrons, so it has to lose 2. That means once it loses 2 and it looks like neon, yay, it'll have a +2 charge. And it'll behave, the ion will behave like that, and it has an oxidation. Has an oxidation state of +2, and that process is called oxidation. Aluminum, notice, is still a metal. It has 3 valence electrons. If it loses 3, it will look like neon. Yay! It'll have a +3 charge, and again, that process is called oxidation. If you were to write what this looks like, we start out with the atom and then as the reactant, and then the product will be the ion with the lost electron. E to the -1 is just a symbol for electron. Remember, electrons have a -1 charge. Magnesium, on the other hand, has to lose 2 in order to look like a noble gas. So this is how it'd be written. You'd be left with magnesium and those 2 electrons out there for someone to pick up. And we'll talk about who will pick them up in just a minute. And aluminum, 3. Okay, so in summary, metals lose electrons. This is called oxidation. The most common ions charge is called its most common oxidation state. Now, what about nonmetals? Nonmetals are actually look really close to noble gases. They're not going to want to lose, they're going to want to gain. Let's go through nitrogen. So nitrogen has 5 valence electrons. Remember, we want to get to that octet. If it gains just 3 more and becomes 2p3, it will look like neon. Okay, so it's going to gain 3. The other option is for it to lose 5, but it has an option. Lose 5 or gain 3. Gain 3 is easier. When you gain 3 negatives, you become -3, and that's a process weirdly called reduction. Now, where's it going to get these electrons from? Well, maybe from aluminum that just lost the 3, as you recall, of the metals. Now, for oxygen, it needs just 2 more to get that octet, those 8, and fluorine 1 more. So you can see that oxygen is going to gain 2, fluorine 1. The ion will be -2 for fluorine, -1. And again, this is reduction. Now, everything in nitrogen, oxygens, and fluorine's family acts the same way. So chlorine would gain 1 as well, so that it would look like the next noble gas, which is argon. Sulfur would gain 2, and it would also want to look like argon, but it has the same pattern. That's why this periodic table is really useful in predicting the ion that each one of these elements will make. And again, reduction is the gain of electrons to form an anion, a negative ion. Nitrogen needs 3. It'll pick up 3. Where does it get it? Maybe from aluminum, maybe from 3 separate sodiums. But once it gets them, it'll look like a noble gas. Similarly, oxygen just needs 2. And then it will look like a noble gas, and fluorine will pick up 1, and then it will look like a noble gas neon. It'll have the same electron configuration as neon. So in summary, nonmetals gain electrons. This is called reduction. The most common ion charge is called its most common oxidation state. Now, a way to remember that metals are oxidized and nonmetals are reduced is this 2 acronyms you can remember. Either oil rig, oxidation is loss of electrons, OIL, reduction is gain of electrons, RIG, or Leo the lion says grr. So Leo is lose electrons, oxidation, and grr is gain electrons, reduction. And again, you're going to need to remember, it's just a prediction. Now that we understand it, we can predict the ion charges that each one of these families, columns of elements form. If you're in group 15, you're going to form a 3-. If you're in group 17, you're going to form a 1-, because if you add that many electrons, you will look like a noble gas. So that is your lesson.